Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for January 23rd, 2013.
On this week's show, NASA beams Mona Lisa to the moon, Graphene Plasmonics beat drug cheats, a metamaterial sensor provides bigger picture, and nanowire solar cells soak up sunlight.
NASA recently demonstrated the first one-way laser communication at planetary distances. Scientists with the Lunar Reconnaissance Orbiter, or LRO, beamed a digital image of the Mona Lisa nearly 240,000 miles from Earth. The image was sent from the Next Generation Satellite Laser Ranging Station at NASA's Goddard Space Flight Center in Greenbelt, Maryland, to the Lunar Orbiter Laser Altimeter instrument on the LRO. By transmitting the image piggyback on laser pulses that are routinely sent to track Lola's position, the team achieved simultaneous laser communication and tracking. Typically, satellites that go beyond Earth orbit use radio waves for tracking and communication. LRO is the only satellite in orbit around a body other than Earth to be tracked by laser as well. Mona Lisa's image was divided into an array of 152 by 200 pixels. Each pixel was transmitted by a laser pulse, with the pulse being fired in one of 4,096 possible time slots during a brief time window allotted for laser tracking. The complete image was transmitted at a data rate of about 300 bits per second. Once the image was sent, it was corrected for transmission errors caused by the Earth's atmosphere using common techniques used in CDs and DVDs. The final image was verified when it was returned to Earth using LRO's radio telemetry system. The project was accomplished without interfering with Lola's primary task of mapping the moon's elevation and terrain. The achievement sets the stage for the Lunar Laser Communications demonstration, a high data rate demonstration that will be a central feature of NASA's next moon mission.
A simple optical system using graphene plasmonics can potentially see a single molecule and analyze its composition within minutes. The advance could lead to more sensitive drug testing of professional athletes, a topic much in the news these days. The new type of sensing device, developed in England and France, employs topological properties of light phase to identify an attachment of just one relatively small molecule. Singular optics that use the unusual phase properties of light is an emerging field of research, and this work shows how it can have practical applications. To test the devices, the team covered them with graphene. Next, hydrogen was introduced, allowing the devices to be calibrated with sensitivity 3 orders of magnitude better than existing models. The breakthrough could be applied to sensing explosives or to detecting viruses, but the team said they're only starting to scratch the surface of possible applications. The findings were reported in Nature Materials.
A new type of lens developed at Duke University compresses images more efficiently than current methods because the metamaterial sensor does it as they are being recorded rather than after the fact. Because of the properties of this man-made material, much of the additional equipment needed for conventional detector systems, like lenses, mechanical positioners, and data storage or transmission devices, are not required. The findings suggest that cameras, X-ray scanners, and other imaging technologies built using the sensor could take pictures faster and with fewer measurements or detectors than currently needed. The material is a thin laminate with row upon row of tiny squares etched onto copper, each one tuned to a different wavelength. The material is flexible and durable enough to be attached to a wall, wrapped around corners, or even laid on the floor like a rug, making it an inexpensive alternative for a variety of sensing applications. The new system works with microwave light and produces 2-dimensional images. The team is currently exploring moving the technology to 3-dimensional capability in real-world settings. The findings appear in Science.
In a demonstration of how photonic effects at the nanoscale can improve power conversion efficiency, a new nanowire-based solar cell absorbs more sunlight than conventional ones. Solar cells made from arrays of indium phosphide nanowires are thought to be more flexible and cheaper than conventional cells, but they do a poor job of absorbing light. A team at Lund University showed that arrays of phosphide nanowires on solar cells can be optimized by varying their diameter and length. They built a solar cell with such nanowires that converted 71% of sunlight into energy. Until now, the dream was to attain 10% efficiency, but the Lund team reported an efficiency of 13.8%. They also showed that the nanowires can generate power at the same level as a thin film of the same material, even if they only cover around 10% of the surface rather than 100%. Further research will explore how to make the cells larger and determine cost and durability. The work appears in Science.
Well, that's it for this edition of Light Matters, Photonics Media's weekly newscast.
Write to us with your comments or questions at lightmatters@photonics.com.
And we hope you'll come and see us at booth 8600 at the BIOS show and booth 600 at Photonics West, where you'll have a chance to appear on camera and possibly on a future episode of Light Matters.
We'll also have an interactive game on photonics trivia called Light Masters, and you could win a Google Nexus 7 tablet.
Thanks for watching, and we'll see you next week.
In this experiment, we have a single scattering metallic object moving through a reflectionless room. On the left is an optical video of the scene, and on the right is the reconstructed 2D image from the metamaterial imager. The metamaterial imager only sees objects that are reflective to microwaves. When the reflective object moves into the field of view of the metamaterial imager, we see the corresponding pixels in the reconstructed image light up in the right figure.